Modern retail systems need to process terabytes upon terabytes of JSON data daily to extract critical business information. But when records can exceed 1 gigabyte each with deeply nested data, CPU processing can become inefficient and costly. In this video, let's learn how Nvidia was able to reduce processing time by over 75% to cut down on costs. JSON, or JavaScript Object Notation, emerged in the early 2000s as a simple text format for web data exchange, back when flip phones were cool and MySpace was still a thing. Its key value structure with support for nested objects made it ideal for representing complex data hierarchies. Today, it's a default for web API standards. As companies accumulate billions or trillions of these records, with some exceeding 1 gigabyte in size, running a single server to process these records would take forever. This is where Apache Spark comes in. It distributes processing across multiple machines, handling massive JSON datasets through its SQL interface. Each Spark application has 3 main components. The driver, which is the brain of the operation. It breaks down your query into smaller tasks, schedules them, and coordinates execution. Then there's a cluster manager, which allocates resources in the cluster, ensuring tasks gets the compute power that it needs. The executors, or the workers that actually process your data, they run on different machines in the cluster in parallel. After processing, results are sent back and combined at the driver. Apache Spark's SQL provides the getJSON object function to extract data from nested JSON structures. For example, to extract, let's say, the customer's name from this JSON object, we start with the $sign symbol, which represents the root of our JSON document. Each level of nesting is separated by a dot. For nested fields that contains array, we can use the square brackets with the index number or a wildcard star for all elements. Nvidia found that sometimes a single query can contain up to 50 of these function calls. Now imagine with billions of these JSON documents, the CPU might just start sweating like a developer during a P1 prod issue. Nvidia solves this by creating Rapid Accelerator for Apache Spark by leveraging GPUs. Without going into much details, the difference between CPUs and GPUs is that CPUs are designed for general purpose computing, handling complex tasks like running your OS and applications. GPUs, on the other hand, excel at performing simple calculations on massive amount of data in parallel. The Rapid Accelerator automatically intercepts Spark operations that can benefit from GPU acceleration. It then processes thousands of JSON documents at the same time across thousands of GPU cores. It also handles data transfer between the CPU and GPU memory. The best part is that it requires no code change to existing Spark application. When the team first implemented GPU processing for their JSON data, they encountered a series of interconnected problems that actually made the process slower than CPU processing. For context, in Nvidia architecture, GPU has thousands of threads that can work in parallel. These threads are organized in a group of 32 called warps. Each warp's thread must execute instructions in lockstep, sharing a small but extremely fast memory called the L1 cache. Initially, they assigned one JSON document to one thread for processing. However, when these JSON files are several kilobytes in size, and when different threads are processing different documents at the same time, they all end up competing for the same limited L1 cache space. This led to a performance problem called cache thrashing, where the GPU constantly had to erase and rewrite data from the L1 cache to a slower memory. The second issue involves how threads within each warp must execute in synchronization, meaning threads process different JSON documents that run against the same query. If a single thread is unlucky and it runs against a very complicated JSON, this thread ends up grinding away while other threads are chilling and enjoying a cold one with the boys. The final and perhaps the most significant challenge lay in the nature of the data itself. Their analysis revealed that 85% of JSON fields that they were querying appear in less than 0.01 of the records. This extreme sparsity meant that most threads were searching for fields that rarely existed, leading to highly inefficient processing patterns. When combined with the warp synchronization requirements, this sparsity caused intensive delays as threads frequently diverge in their execution path. The GPU, which were designed for parallel processing, was essentially being forced to work sequentially due to cache limitation, thread divergence, and sparse patterns. They first reanalyzed how JSON queries were being processed. They discovered that when multiple queries target the same JSON document, they could group these queries together within the same warp. This simple change meant that threads within the same warp could work on related data, significantly reducing thread divergence and resulting in 3.2x performance improvements. However, they still noticed that even with grouped queries, thread divergence could still occur when similar JSON path queries were scattered across different warps. Their solution was to first sort the queries lexicographically before processing. This sorting meant that similar queries would naturally group together, further reducing thread divergence and improving cache utilization. This additional change brought another 10% improvement. Another cool optimization was reimagining how they parse JSON strings. In the initial approach, processing happened sequentially, so given this JSON, it would first read the open curly bracket to identify the start of the object. It then reads the double quote, start of the key, read the P, the R, and so on character at a time. This sequential processing meant that even with multiple GPU threads, each thread was still reading and interpreting character one at a time. The new approach uses parallel tokenization. For example, if you're searching for inventory.quantity, multiple threads can identify inventory as nested object, locate quantity within it, and extract the 100 without waiting for character by character parsing. This approach allowed the team to process multiple characters at the same time, taking full advantage of the GPU parallel processing capabilities. Early benchmarks showed that this change could provide an additional 50% improvement, potentially reaching up to 5.6x improvement overall. The team is also working on extending the parallel processing techniques for JSON to other string-based operations in Apache Spark. This includes regular expression, string matching and comparison operations, text parsing, and analysis functions. Well, maybe it's time for me to buy more Nvidia stocks since they're just gonna take over the world. What do you guys think of their implementation with JSON? As always, thank you so much for watching and see you in the next one.